On today's video, we're going to look at color bars. How's that sound? We're going to look at color bars today. No, actually, we're going to look at something a little different. Today, we're going to look at a CRT TV, and I'm shooting this a little differently. The picture probably looks a little different from other videos because I'm shooting this on tape. We've gone back to the future. I'm shooting this on high definition tape. The reason why is I need to use a CCD camera to photograph a CRT. The problem with CMOS cameras is that phenomenon that's referred to as rolling shutter. You can't get a good picture on a CRT. And how can I show you the problem that we're experiencing on this TV if we only have half a picture? The big difference between a CMOS and a CCD, if you want to go into the technical details, is that a CCD takes the entire image at once. It snaps an entire picture. All the lines are stored at the same instant in time, and then they are read out line by line. And in the case of, this is actually a 1080i camera. And some people will argue that 1080i or 1080 interlaced was not as good as 1080p. But that's not actually the case, because the sensor takes the shot all in the same 1/60th of a second. It doesn't matter whether you read out the lines 1, 2, 3, 4, 5 all the way to 1080, or you read the even numbers 2, 4, 6, 8, 10, and then 1, 3, 5, 7. It really doesn't matter what order you read out the lines. You can read them out in a totally random pattern. It doesn't matter as long as they all arrive at the screen at the same point in time and they're all reassembled at the same time. But this has been an argument that's been going on as long as high definition video has been around. It goes back to the analog days of VHS tape and analog cameras that read out, basically Vidicon cameras that read out one line at a time. You would have what was called field slippage. So movement that occurred from between one frame and the next could cause jaggy lines. And when people saw the difference between a 480 progressive from a DVD, which was taken off a film source, and a 480i from a tube-based camera that was scanning line by line, there was a noticeable difference. In the digital world, it's not really that big a deal because the CCD is capturing all 1080 lines at the same point in time. But where it does make a difference is if you're shooting a CRT screen, a rolling shutter from a CMOS camera will give you, well, you've seen the picture. You get half the picture, or just half the picture blanks out. And the reason why is a CMOS camera, the shutter is only open at the line by line. As it's scanning, it'll scan all the lines one at a time, but the actual, each picture line is only active at that instant. So a phosphorus screen such as a CRT is refreshed by the scanning beam. It actually is out. It's line by line, but the persistence of vision causes this to look like a picture, but it's actually not. And a CMOS camera will actually capture that scanning line, whereas a CCD camera, the shutter stays open for the entire 1/60th or 1/30th of a second and captures the entire frame, more like the eye does. So we're back to the future. We're using a CCD camera to shoot this video because it's the only way I can show you what the picture looks like. And you've probably seen the problem already without me explaining it. We have heavy lines at the top of the picture. You see this? This is called vertical fold over, and it's going to be a capacitor in the vertical sweep circuit. Let's take the back off this set and let's see what the problem is. For the record, this is Toshiba. It's manufactured in 2005, so this would have been right near the end of the CRT era. It's a 10-year-old TV now, 11 years old. Hey, it's still got a great picture. The only reason I'm hanging on to a set like this, I found this set at the side of the road. The only reason I'm going to hang on to a set like this is I use these type of TVs for my security cameras, just for monitoring my cameras. I only need a standard definition set. And a tube TV, I can see it from any angle. Whereas an LCD TV, if I'm off at an angle, the picture is not as good. It's either dim or it's washed out. I can have my security camera monitor sitting up in the corner, and I can see it from any angle. So that's why I still use some CRT TVs around here, and I collect these old ones because you can't get them anymore, and they've still got a purpose. So this is going to be, as I say, a capacitor. Let's get the back off this set. So these long screwdrivers came in handy. I was taking the backs off these old beasts. Okay, once all the screws have been removed, the back will simply lift off. One thing I noticed on this TV, this being a late model CRT set, it actually has component inputs, but don't be confused. They're not a high definition input on this set. It is only a standard definition television, but the component input would allow connection to a DVD player. Whether this set would display progressive scan or not, it probably only displays interlaced. Some TVs would display progressive scan, but I don't believe this is one of them. You need a dual frequency sweep set, and they were generally high definition TVs that did that. So we've got the back off the set. Let's examine this circuitry and see where our problem is. So the board slides out, and let's examine the circuitry. One of the things you'll notice when I'm dealing with a professional camera is this is all manual focus, so I actually have to focus the camera manually. This was one of my professional production cameras when I was in the production business, and this is one that I made a living with. And very, very good quality camera, and I'm not going to let this one go because I paid a small fortune for this camera. This camera cost about 3 times the price of my 4K camera that I shoot with now. It only is a 2K picture. That's not even that. I think it's only 1440 by 1080. It's not even as high a resolution as my other little $200 camera, but it does have a really nice picture. And it's got superior color being a 3-chip camera. Let's explain the components in this set here before we get too involved in it. So we have our power supply over here. This is a switching power supply on this unit. So here's the little transformer here. And the regulator for that would be the chopper transistor. I'm just looking for it. It's going to be mounted on the back side of this heatsink. We know we don't have a problem there. We have a problem in the vertical circuit. So let's break down these circuits. We have our audio circuit over here. This is our analog tuner and our analog video inputs. Video in, component in, S video in, audio amplifier. We have our vertical circuit, which is right here. And our problem is going to be somewhere in this circuit. Now, how I know that this is the vertical circuit is because this coil here, or this plug, this is where our yoke coil is plugged in. This is our horizontal linearity coil over here. This is our flyback transformer where the high voltage is generated, and our focus and screen controls are here. And here's our interconnect to the CRT that sends our video signal and our screen voltages and so forth up to the neck of the CRT. Our high voltages for focus and screen come in on these 2 red leads that come right off of the flyback transformer off the focus screen resistor. This is again our horizontal linearity coil. Our horizontal coil is typically going to be the red and blue wires, and that's why they're separated, because there's about 1,000 volt pulse on here, and our yellow and brown wires here, these are going to be our vertical, which go to this side of the plug. So that would make this IC here our vertical output IC. And we can confirm that if we look down on the board here, look real close down here. Here's our vertical size adjustment control here. Our problem on this set is going to be in the vertical circuit, and it's going to be a small capacitor. Guaranteed it's going to be a very small capacitor that's bad, probably in the 1 or 4.7 microfarad range. It's a capacitor called a bootstrap capacitor. Seen it a zillion times on Toshiba. Never worked on this particular model of set before. So we're going to get in here, we're going to use some test gear and look at the vertical pulses going to this vertical output IC. This being a AC powered hot chassis set, we're going to use the isolation transformer. I should not say it's a hot chassis set, because it does have a transformer over here, right? It is the DC side is isolated, but there is a hot side to this chassis, so we are going to be using an isolation transformer for safety. Some of the other circuits on this set I'll point out on this thing here. Turn the circuit board around here. We've got ICs on the bottom of the board. This is a late generation analog set, so they had gone to flat pack ICs. I'm just going to unplug the degaussing coil, which is this red wire here that's going up to the coil on the picture tube. This is a degaussing coil. What this does is when you first turn the TV on, this creates a weak magnetic field, an AC magnetic field that falls off relatively slow to demagnetize the picture tube, and it plugs into the board down here. We're just going to unplug that just to give me a little bit more slack on the wires here, so that I can turn the board over and we can examine the bottom of the circuit board. Now you might wonder, why is there a big hole in the board here? Well, because they don't like to waste materials when they're manufacturing televisions. You will notice that the cutout for the board for the CRT is actually from that area of the main board. So it's all etched on one, and that piece there, it's turned over, but that piece comes out of there. It's inverted though. Anyway, on the bottom of the board here, we have our basic single chip solution. This is your Lumichroma circuitry. You've got our stereo sound circuitry over here and system control. It's all basically a single chip solution on these. Very modern set, no more through hole for the big ICs. We don't have a problem in any of these, so I'm not even going to get into this. Our problem is strictly vertical on this thing. Very straightforward. In fact, I can tell you what capacitor probably is the fault on the set without even putting any test gear on it. It's probably this one down here. It's either that one or maybe one of these two over here. I can confirm that with the ESR meter, which would be, we'll do that. But let's look at some of the other circuitry on here. This is going to be probably the horizontal drive transformer over here, because our drive signals are all coming off that big IC that's on the back side here. Our chroma circuitry, our comb filter is all in here. This is our crystal for our 3.58. For you guys that are going to be wanting to be precise, 3.5792543 megahertz for our subcarrier regeneration, but we'll round it up to 3.58 just to be, just to round it up. But for the guys out there that want to be precise, it's 3.5792543 for the NTSC system. Okay, we have some diodes down here. This is in power supply. This is one of our main diodes in our power supply here. These are our rectifier diodes from our switching power supply. And this transistor down here is more than likely, I haven't looked at it yet, but this is more than likely our horizontal output. This one here that's mounted alongside of the vertical output IC on this big heat sink. This is more than likely our horizontal output. And if I can confirm, I don't know if I can see it down here or not, but I'm pretty sure that's our horizontal output, because this one here is this one back here is our power supply chopper transistor. Yeah, that's our horizontal output down here. This is our vertical output IC, and that would make this little transformer behind here. This will be our horizontal drive transformer. Let me just get some tools out here and we'll run some tests. Okay, what we're looking at here is we're looking at the scope, the vertical sync pulse going into the IC. This is our vertical pulse here, if I can expand that a bit. But this is our vertical sync pulse going into the IC, so we know that that's good. Just going to take a few more tests on this circuit and see where our distortion's coming in. Okay, I'm just going to check the bootstrap capacitor here. I'm just going to put my probe on here, and as you can see, we've got some distortion here. That should be a nice clean pulse, but you see it kicking back down on the bottom side there. So we've got some distortion on this little capacitor. It is a small one, as I thought it would be. That one looks okay. That's our sawtooth. Let's put some more gain on there, see what it looks like. Okay, we can see some distortion on here too if you look. If I can trigger my scope properly here. Come on, trigger. There we go. There's some distortion. You see that? That signal is not looking good. It should be a nice sawtooth, and there's some more. This is again, we're going into the same. You can see the wave. You can see the wave dipping. That says the signal is folding over on top. And we look back here, and I'll show you which ones I'm looking at here. And then again, you can see the little peak there. Right here, right? It should be nice, clean sawtooth, and it's not. I'll show you the parts that I'm testing, I'm scoping on this thing is right on the bottom side of this board. Whoops, gotta focus the camera there. There we go. So the capacitors I was scoping were these ones here. These two little ones here. That one and that one. Those are the two that I was scoping. And we'll put the ESR meter on there and actually look and see how the ESR looks on those parts. So the two capacitors I was scoping is these two down in here. That one and that one. These two. They are, can barely see this thing. It's not that it's dusty, it's just awkward. C406 and C407. This one's C408. C406 and 407, these two little small buggers in behind here, those are the ones, and it's the small one here, actually 406, the one in the back, this is the one that I was getting the distortion, the most amount of distortion on. So that's the first one I'm going to check. We'll check the ESR on that capacitor there and see whether that is the culprit. More than likely it is these type of vertical fold-over problems. It's typically a small capacitor. It's called the bootstrap capacitor, and why they call it that, that's what it's called. Anyway, let's check the ESR on that capacitor and replace it. We'll see if that fixes the problem. But we'll check the ESR first. So here I got the ESR meter. I've zeroed it out. So it's ready to go. We'll test them both. I think they're probably both going to be bad. But that one there is measuring 4.6 ohms. I think it's probably a little bit high. And this other one here is completely open. This one here is okay. So both of these little capacitors are bad. Let's change them. One, and these are polarized capacitors, so you have to get the polarity correct on them, otherwise you're going to have a problem. Here they are, they're both out. Let's take a closer look at them and see what they look like out of circuit. So the first one I'll look at is C406, which is the smaller of the two. This is the 1 microfarad at 50 volts. A 1 microfarad at 50 volts actually should be better than 16 ohms. I think it probably is, but we're going to change it anyway just because this one goes bad. It's coming up at 4 ohms. A new one's probably going to measure a lot better than that, but let's take a look at this one. This one was measuring open. This is a 100 microfarad at 35 volts, sorry. 100 microfarad at 35 volts should be no worse than 0.32 ohms ESR. Open. This cap is completely open, but I am going to change both of them just because I've got them out of the circuit, and I know that the little 1 microfarad does give some problems. So we're going to change them both, just because when I do put this monitor into service at some point, I want it to run for a while. Now remember, I showed you the 1 microfarad before, the old one here, even though it says worst case would be about between 14 and 16 ohms, and this one here is measuring up at 4.9. But here's a new one. Okay, a new one's 3, so it is starting to go a little higher. Here's the 100. The other one was measuring open. Here's a 100.2, and a 100 says it should be no worse than 0.32. So we're at 0.2. So there's our new capacitors here. Gone a little bit up in the voltage on them. I went to a 50 volt because I didn't have a 35, so a 50 will be more than enough headroom here. Let's get these new components mounted on the board here. And of course my neighbor's gonna start mowing his lawn when I'm making a video. How dare him fire up his gas powered lawnmower. Okay, our polarity on here. Let's get the camera zoomed in here. We'll get the camera focused. There we go. Polarity. Positive is towards the back. You can see the positive terminal here. I'll just point that out. Just going to get rid of my scope probe here. I don't need this thing here anymore, and I don't need to lose it. So let me just get rid of my scope probe. There, that's out of the way. The positive terminal is to the back, as you can see. The longer lead is positive, so we'll put the 2 capacitors in place. Turn this set back over and we'll see whether we solve the problem or not. Just gonna plug my speaker wires back in. I unplugged the speakers there so that I could work on it. Plug the degaussing coil back in over here. Reconnect the cable and see what it does. Slide the circuit board back into the track. There we go. I would say we fixed it. Let's just adjust our screen a little bit on here. I think our screen may have got bumped down a bit. So we'll just adjust the screen and the focus. There we go. No more fold over at the top of the screen like we had before. Looking good. That's how it should look. I hope you enjoyed this throwback look at technology. And I know there's going to be a few of you trolls out there that are going to be critical about why anybody would fix an analog monitor. As I said before, these things still are good for certain things, like security monitors and other applications where you need a wide viewing angle and you wouldn't necessarily use plasma or something like that could burn. I mean, these will burn too, but I've got several CRTs that have got nice images burned into them from running on security cameras. But they do a good job, and they are readily available. And you know what? The best part of all, they're free. People are giving these things away. They want rid of them. So there you go. That's how you fix a CRT with a vertical problem. 2 capacitors in the bootstrap. We'll review which ones failed. There's the 2 problem caps there, C407 and C408, a 1 microfarad 50 volt and a 100 microfarad 35 volts. Both of them were just standard 85 degree capacitors. I did replace them with 105 degree. A lot of the older Toshibas, these capacitors were red in color. And the red ones in some of the older ones were actually a special cap at the time. And you had to order them from Toshiba. That was because that was back in the days when 105 degree low ESR capacitors were not common. And some of the earlier, and when I say earlier, I'm referring to sets made in the late 80s, early 90s, used those red colored capacitors, and they would actually be leaking. The plug on the bottom was all soft and the electrolytic was leaking out of them. And we had to order the original one from Toshiba because a regular capacitor would fail very, very shortly. But you can, in the case of the Toshiba with the red caps, you can use 105 degree and they will work just fine. But back in the 80s when there was no 105 degree other than the ones obtained from Toshiba, yeah, if you put a regular one in, you'd be changing it every couple months. But these ones here, I've put 105 in now. They'll be good for another 100,000 miles. We'll catch you in the next video. Thanks for watching.